for everybody else to join in. So very crucial lecture for us today with the further study of work power energy. So today mostly we'll be discussing about the applications of work energy theorem that we have discussed here last time. The statement of work energy theorem being that the net work done by external forces plus non-conservative forces on a system equals to the change in kinetic energy plus the change in potential energy. So we will be discussing about applications of them. So this is session number 3 of work power energy for us. Yes, I will send you a list of questions, Vaishnavi. In fact, today we will be solving some of the questions in class itself from HC Verma. So we'll just wait a minute for a couple of for some of the students to join in, and then we'll start. Okay, so let us begin. So we'll start with a very quick recap of the things that we learned in work energy so far. So we understood that the definition of work done by a force, okay, it is the proper definition is path integration of force or F dot ds integrated from initial to final. But however, we saw that in this, if the force is a constant force, that is constant in both magnitude and direction, then in that case, the F dot ds integration becomes simply dot product of force and displacement. But that is only if this is the case, if the force is constant. Otherwise, we have to always calculate the work done by the force by the integration method. Okay. Then based on this, we also saw that we can define forces in two categories: conservative and non-conservative. Okay. So we saw that For conservative forces, the work done is path independent. Okay, and the work done in a round trip is zero. Round trip being when the path is a closed loop, so your initial position and final position are the same, then by definition the work done by a conservative force has to be zero. Whereas when we talk about non-conservative forces, the work done is path dependent. Okay, and we'll discuss more about this today. Okay, so the work done in a round trip, in the case of a non-conservative force, is going to be a non-zero quantity. And based on that, we had seen a couple of examples that spring force is conservative. Any constant force is conservative, etc. Whereas we had seen that kinetic friction is an example of a non-conservative force. And then based on the definition of conservative and non-conservative forces, we came to the definition of potential energy of a system. And we had seen that the potential energy is defined as the energy associated with the state or configuration of a system. So whenever we are changing the state or configuration of a system, we have to do work against the internal conservative force. So the amount of work done against the internal conservative force is nothing but negative of work done by internal conservative force, and that is equal to the change in potential energy. So delta U, which is the change in potential energy, equals to the work done against a system's internal conservative force. Okay, to change its state. When we want to change the state or configuration of a system, to do a certain amount of work against the internal conservative forces of the system, and that contributes to the change in potential energy. And from this, we had seen the general definition of work energy theorem, which is defined for a system, that is the sum of work done by external forces plus the work done by non-conservative forces equals to the change in kinetic energy plus change in potential energy. We can also convert this to this, which becomes the work kinetic energy theorem, because this is negative of work done by the internal conservative forces. Okay, if you apply this definition over here, delta U is equal to negative of work done by internal conservative forces. So the statement then becomes work done by external plus work done by non-conservative forces plus the work done by internal conservative forces is equal to the change in kinetic energy, or the net work done is equal to the change in kinetic energy. So this was the work kinetic energy theorem, which only dealt with work done, that is the net work done by all the forces acting on a body with respect to the change in its kinetic energy. But a better way of expressing a similar theorem is to define a system, and instead of defining the net work done, just to define the work done by external forces and non-conservative forces, and then define the change in potential energy of the system. Okay. So the kinetic energy plus potential energy together is called the mechanical energy of the system. So change in kinetic energy plus change in potential energy is also referred to as the change in mechanical energy of the system. So these are the conceptual aspects that we've discussed in the last lecture or so. I just wanted to bring you up to, yeah, work kinetic energy theorem can be proved by this manner. Okay, we'll come to a more formal proof of it at a later stage. Okay, actually we have proved this theorem earlier, No. We have proved this theorem earlier. We have seen that the net work done is basically net force dot product with displacement integrated, and we saw that that becomes mass into tangential acceleration into ds and all that. So we've already seen the proof of this. Now when you split this into this, work done by external plus non-conservative plus internal conservative, you can show that it becomes this statement. So in a sense that we know the proof of this. Okay, so it's basically a logical extension of the work kinetic energy theorem, which we have already proved earlier. So we don't really need to separately prove the work energy theorem. It's just that some of the terms in the work kinetic energy theorem are redefined. So you are splitting the net work done into work done by external plus non-conservative plus internal conservative forces, then defining this term as negative of delta U, and that's how you get this. So this theorem is basically, the proof of it lies here only in the work kinetic energy theorem, but the term delta U is defined separately in this. Is the point clear, Nikita? Okay. Okay, now when we define potential energy, there are two specific examples of potential energy which are important to us at this stage. Are spring potential energy, which is defined as half kx square, we saw, where k is the spring constant, x is the amount of deformity, and the gravitational potential energy, for which we define change in gravitational potential energy as the mass of the body into g multiplied by delta y, where delta y is the vertical displacement. So anytime a body is having a positive vertical displacement, that means its height is increasing, whatever its path is. But if the body's height is increasing from the point A to the point B like this, its vertical height is increasing by h, then delta U gravitational will be plus mgh, because A to B. And likewise, if it is coming from B to A in the opposite direction, its height is decreasing. So delta U gravitational for B to A will be minus of mgh, because delta y, the change in vertical coordinate or the vertical displacement, will be minus of h. So this is the simple rule of thumb to remember about this. And whereas for the spring, we have the direct formula like this. So the change in potential energy for any situation for the spring will be nothing but half k into final x square minus initial x square. And that is your final minus initial. So these are the two equations or the two formulae that we'll be using in applications. Okay, so having quickly gone through this review of the aspects that we've learned in the last couple of lectures, today we will concentrate on the applications. Okay, so this is the portion of work energy theorem that you have to prepare. I mean, this chapter of work by energy, this is the portion that you have to prepare for the upcoming test on Sunday. There are more things theory wise also, and we will come into that in the next week and further. But as of this week, for the preparation of the upcoming test, this is the concepts that you have to know. Now, how to apply this concept set in most of the cases, we'll discuss some example questions next. So let's start with an example like this. We will see how to apply the work energy theorem in this next example. So what's happening here is that we have a block mass m, which is on a rough surface of coefficient of friction mu, and it is initially at rest. Okay. Now what we do is we start pushing this with an external force which is variable but horizontal. So a variable horizontal force starts acting on the block, which has a mass of, let us say, 5 kilograms on a rough surface, which has coefficient of friction equal to, let us say, 0.2. Okay. So that variable force is given by this formula. Its magnitude is equal to (20) into 1 plus 0.1 s, where s is the displacement of the block in meters and F is the force in newtons. So we have to calculate the work done by the force F through a displacement of 2 meters. Work done by friction through a displacement of again 2 meters. And we have to find the speed of the block at the instant when its displacement is 2 meters. Okay. So let's begin with this simple situation. So we can see that since this is a variable force, how we will calculate the work done by the force? We will have to calculate it by this thing method, the integration method. Okay. So for the first part, the work done by the force F is a variable force. So we'll have to calculate work done as integration F dot ds. Now you can see that as the block moves, if this was the initial position at time t equal to 0, at some general time t, when it has made a displacement of s, it has a velocity v. At that point of time, this force is given by the formula 20 into 1 plus 0.1 s. Okay, and now if it makes a small displacement ds from here to here, so during that small displacement, you can see that this F dot ds is first of all going to be F ds, because force and displacement are along the same axis, the angle is 0, and the force should be substituted with 20 into 1 plus 0.1 s. Okay, so this should be from initial to final position. So initial position is s equal to 0, final position is the final displacement. So in this case, we are calculating from through a displacement of 2 meters. So from s equal to 0 to s equal to 2 meters. So this will give us the work done by the force F in joules, because the force is in newtons and the displacement is in meters. So work done by F is going to become 20 into s plus 0.1 s square by 2 integrated from s equal to 0 to s equal to 2. So that will be 20 into, now the upper limit will become 2 plus 0.2, right, as you can see when you substitute this, and the lower limit will be 0. So the net work done by F will become how much? 2.2 multiplied by 20, so that is 44 joules. So positive of 44 joules is the work done by F. Okay, this is the work done by the force F through a displacement of 2 meters. Right, so I'm just going to minimize this a little bit more so that you can just go through this carefully. Okay. Now, just like I've calculated the work done by F, now next thing you do is you calculate the work done by the friction. Now that's going to be very easy, because friction is going to have a constant magnitude and a constant direction. Okay. Because this is a situation where normal reaction of the block with respect to the surface is not affected by F. Normal reaction is equal to mg. So the friction has a constant magnitude of mu mg and a fixed direction, which is opposite to the direction of displacement. So work done by friction you can just get by the dot product method. Okay, and once you've calculated those two, make use of the work energy theorem to find the speed. So for the speed, you first find the kinetic energy, and from the kinetic energy find the speed. So just note this down and work on the second part, that is the work done by friction. Yeah, Naman, but the work done by friction will be negative. Okay, the work done by friction will be negative. Yeah, so work done by friction will be negative here. That's correct. Minus 20 joules. Okay. So next thing you can see is the work done by friction. So as the body is moving, F is variable, but the frictional force acting, that's constant. No, it is mu mg, because the normal reaction is equal to mg, and the displacement is in this direction. So work done by friction will be minus of mu mg into s. So in this case, it will be minus of 0.2 into 50 into the displacement of 2 meters we have taken. So that is going to be how much now? Minus 20 joules. Okay, so that is the work done by friction. So that's the second part of the question. Okay. So first part, we had got the work done by the external force. Yeah, I'll just verify that. So we had got the work done by the external force F was 44 joules, and this, okay. Now we can see work done by, so for the third part, if we take this work energy theorem, or we can also use work kinetic energy theorem, whichever we like. Either way, because there's no potential energy involved over here, no internal conservative force is there, no, which is doing work. So work done by internal conservative force is zero. There's no internal conservative force doing work. There is okay, so there is no change in potential energy. So basically, work done by F plus work done by friction should be equal to change in kinetic energy. So initial speed was zero. So we want to find out. So 44 joules minus 20 joules is equal to half mv square. So V becomes square root of 2 into 24 divided by the mass, which was 5 kg. Okay. So this much in meters per second. So we'll just quickly calculate this. So square root of 48 by 5. Okay, so that is about 0.3 approximately meters per second. Yeah, we can express it that way also. You can also write this as okay. So anyway, so this is an example of the application of the work energy theorem, or in this case, you can also say it is the application of work kinetic energy theorem, because really there is no potential energy change or there's no work done by any conservative force involved over here. Okay, so hope this example is clear to all of you. Now let's move on to another example. Now in my next example, what's happening is we'll involve a spring. It's coming 3.1, is it? I don't think so. Let's see. Yeah, sorry. It is approximately 3.1. My mistake. Yeah, that's correct. Approximately 3.1 meters per second. Okay, now let's come to the next example. So in this case, now what is happening is that we have a block on a smooth surface, but attached to a spring on this side. Now, initially the block is at rest and the spring is also at natural length position. This is a smooth surface. Okay. Now from t equal to 0 onwards, a constant horizontal force is used to pull the block. Okay. So from t equal to 0 onwards, a constant horizontal force F of magnitude, let us say 15 newtons, starts acting on the block, which is of mass, let us say 10 kilograms, attached to the spring, which has a spring constant of, let us say, 25 newtons per centimeter. So first of all, find the work done by F and the change in potential energy of the spring when the block has been displaced by X. And secondly, find the speed of the block at X equal to 2 centimeters, X equal to 3 centimeters. In fact, we'll do one thing, we'll do a whole series here. So we'll calculate at 1 centimeters, then 2 centimeters, then 3 centimeters, and finally X equal to 4 centimeters. Okay, so let us understand the application of work energy in this particular question. Yeah, this is in Newton per centimeter. The spring constant given is in Newton per centimeter. Okay, so the first part you can see that F is a constant force which is acting. So as the block displaces through X, the work done by F, we can just use the formula F dot S because it's a constant force. So here it will become Fx. Whereas the change in potential energy of the spring will be plus half kx square, because initially the extension of the spring was 0. Okay. So initial potential energy was 0, and at an extension of x, the final potential energy becomes half kx square. Okay. So the change in potential energy is plus half kx square. So that is the first part done. The work done by F and change in potential energy of the spring in terms of the displacement x of the block. So when the block is displaced by x, the spring is also stretched by x only. Okay. Now for the next part, we can use one of two approaches. Okay. So for the second part, the first approach we can do is we can take a system as the block plus the spring. Okay. So for this system now, the spring force is becoming the internal conservative force. Okay. F, mg, and n are all external forces. Okay. And non-conservative force is not there. It is absent because there is no friction. Okay. Now, as the block is moving horizontally, you can understand that spring force is going to do work on it, but it's an internal conservative force. Normal reaction and mg are not going to do any work. Only F is going to do work because the displacement of the block is in this direction. Okay. So we know that work done by normal reaction is 0, work done by mg is 0, work done by F is equal to Fx. So in general, the total work done by external force is nothing but work done by F, which is Fx. Now plus Fx. Okay. We know the change in the internal conservative force is the spring force. Okay. So we know that the change in potential energy of the spring is plus half kx square. Okay. So when we write, whereas the work done by internal conservative force, sorry, by the non-conservative force, that is 0, because there is no friction present. So starting from this position where the spring is in natural length and the block is at rest and this force starts acting on it, to a position where the spring is stretched by x. Okay. So therefore the block is also displaced by x. And by now it has picked up a speed of v under the action of this force. Our work energy theorem, statement of work energy theorem, okay, which is the work done by external plus work done by non-conservative, is change in kinetic energy plus change in potential energy. So in this case, this theorem reduces to this, that work done by F is equal to change in kinetic energy plus change in spring's potential energy. So from here to here, you can see the work done by F is plus Fx. The change in kinetic energy is half mv square because initial kinetic energy was 0, and change in potential energy of the spring is half kx square. So this is how we will get b as a function of x now. We will see that this becomes fx minus half kx square, the whole thing into 2 by m square root. So this is v as a function of x. Okay, and we can substitute the different values of x here and find out the speed of the block. So this is the main thing over here. This is the application of the work energy theorem. Applied to this particular system that we have talked about earlier. Okay. Now, for example, in the A part, we have to calculate the speed at x equal to 1 centimeter. Okay. And for that, remember, F was 50 newtons, K was 25 Newton per centimeter. Okay. And mass of the block was 5 kg. Okay, so we'll substitute all these things here. Sorry, mass was 10 kg. Okay, so when we substitute, we have to be a little careful about the units. So we will become square root of 2 by 10 kgs into F, which is 50 newtons, into X, which is 1 centimeter. So this minus half K. Now K will have to be substituted in Newton per meter. So 2500 into X square, which will again have to be substituted in meters. So the speed will become like this. Be 0.5 minus, it become 125 into 10 raised power minus 4. So 0.125. Yeah, I'll show the question again. Okay, so a constant force of 50 newtons starts acting on the block of this much mass with spring constant this much. And initially the spring was at natural length and the block was having zero speed. So starting from rest. So we have to find the speed of the block at various different values of x. So to find the speed of the block in general as a function of x, we apply the work energy theorem. So when we apply the work energy theorem, you can see that the work done by external force for my system is nothing but work done by F. So this term is the work done by F, which is equal to Fx because it's a constant force plus Fx. Okay, this term is zero because there's no friction involved, and this term is the change in potential energy of the spring. So that's how I get this equation, and from this I get this equation. So this is giving me V as a function of x. Now we have to just substitute the different values of x given in the question, okay, to find the values of V. Okay, so the first value we have substituted is this one. Okay, 1 centimeter. So we have got this. Now similarly, when we substitute x equal to 2 centimeters, we'll get the value of v like this. Okay, so this you can see will become 1 minus, now this will become 25 into 2, so that's 50. Okay, into, so this will become 0.5 finally. This will become so much. Yes, that's correct. Okay. So if you calculate this numerically, this is approximately 0.27 meters per second. Okay. If you calculate this, it is approximately 0.31 meters per second, or actually 0.32 meters per second. Now, interestingly, when you calculate for x equal to 3 centimeters, we'll do the calculation, but it will come back to the same value, 0.5 root 3 by 10, or approximately 0.27 meters per second. So when you complete this calculation, you will see it will come to this only. Yes, it will come to this. Okay. No, Kevin, x equal to 3 centimeters is possible, and I'll explain why it's possible. Okay. And yes, very good. The fourth part you will get as 0. Okay. So I'll explain why this is happening. You'll understand in a moment why this is happening. So if you put x as 4 centimeters, okay, I'll just save you some time and just give you the answer here. You can check this later. It will come out to be 0. So don't worry about this calculation. You do this calculation later. Complete this calculation part later. Okay. Now let me tell you the logic of why this is happening. So if you understand logically what is happening here is, okay, so take down those values later. Don't worry about that just now. Okay. So what is happening is when we are starting from u equal to 0, x equal to 0 position, this force that we are applying now is giving the maximum acceleration. And that maximum acceleration you can see is F by m. Okay. Whatever that F by m was, in this case it was 5 meters per second square. Now from here, suppose we are at some value like this. Okay, so by now it's got some speed v, but it's also got some x, but it is such that suppose kx is still less than f. Okay. So if you calculate this kx being less than f, you will get the condition that x is less than 2 centimeters. So at that point of time, what is happening? The external force is greater than the spring force. So what is happening? The acceleration is in this direction. So for x less than f by k, the speed is increasing. Okay, but the moment we cross the point, or first let's say we reach a position where momentarily the acceleration becomes 0 in this. Okay, why? Because f is equal to kx at this point of time. So when you solve this, x will be 2 centimeters. So at x equal to 2 centimeters, momentarily the acceleration is 0 because these two forces are cancelling each other. Okay. Now what happens after this is that, now see, you might say if the force is 0, acceleration is 0, why is the block going further? Because it already has momentum. See, it's already got some velocity because from here to here the speed is increasing continuously. So therefore, even though the acceleration has become 0, it has to continue straight beyond that. So now it's reached a stage where what is happening? X has become greater than f by k. Okay, or basically kx, the spring force, has become greater than f. So when you solve that, that will give you the condition that x is greater than 2 centimeters. So now what is happening? It's decelerating. Okay. It's continuing in the same direction, but it's decelerating. So this is when the block starts to decelerate. Whereas here the block was accelerating. Here the block was accelerating. Okay. So when it reaches this position, it is at equilibrium. So its speed is maximum because after this it's decelerating. Okay. So you can see for x equal to 0 to 2 centimeters, what is happening? Your f is dominating over kx. So the acceleration is positive. So speed is increasing. Okay. But for x equal to 2 centimeters onwards, okay, what happens? That is x greater than 2 centimeters, kx dominates over f. So the acceleration becomes negative. So the speed starts decreasing. Okay. And because the speed starts decreasing, obviously it will reach some stage where the block will stop. So momentarily the speed becomes 0. But at that point of time, x is maximum. No? So it will have maximum backward acceleration. Okay. So this is when the block would have reached the maximum displacement. Okay. So x becomes the maximum value when v becomes 0. So when v becomes 0, you can see that half mv square plus half kx square was equal to fx. So when v becomes 0, x is becoming x maximum. So what is happening? Half kx maximum square is equal to f into x maximum. So how much is the value of this maximum x? It is 2f by k, which if you calculate is 4 centimeters. So it's not surprising that we had got the value of velocity as 0 at 4 centimeters. So now what will happen after you cross this point? I mean, after it reaches 4 centimeters, now it will accelerate back. So as long as we keep applying this external force, the block will keep oscillating between x equal to 0 and x equal to 4 centimeters. Understood now? And as it oscillates, every time it goes through that 2 centimeter position where the forces are balanced, it has maximum kinetic energy. Okay. So here the block will oscillate. Now it will tend to come back because of this acceleration. So it will tend to have a velocity in this direction. Okay, till it comes back right to the natural length position, where again its velocity becomes 0. So it keeps oscillating. So the block oscillates continuously between x equal to 0 to x equal to 4 centimeters. Okay, and when it is at x equal to 0, every time it's at x equal to 0, its speed will be 0. Every time it's at x equal to 4 centimeters, its speed will be 0. Whereas in between, at x equal to 2 centimeters, its acceleration is 0, but speed is maximum. And that maximum speed we saw is square root of 0.1 meters per second. So it keeps backing and forthing as long as we are continuously applying the force, capital F. Okay, so Kevin, I hope you have understood this point here, why it's going beyond the 2 centimeter position, even though Kx is balanced by mg at 2 centimeters. So it's basically an oscillation like this. Okay, so don't worry about the values. You can go through it later when I send you the notes. But this is actually showing us, and another interesting thing it's showing us that the speed was same at 1 centimeter and 3 centimeters. See, you got the same value of speed at 1 centimeters and again at 3 centimeters. Why that was the case? Because 1 and 3 are symmetric with respect to the mean position of the oscillation, which is 2 centimeters. So there is a symmetry. So that symmetry is like this, that if this is the x equal to 0 position, here speed is 0. If this is the x equal to 2 centimeters position, then whether it's on its way away from or is on its way back to, it will have the maximum speed, which is square root of 0.1 meters per second. And similarly, by the time it reaches x equal to 4 centimeters, again its speed becomes 0. Okay. So again, at two symmetric points like this is x equal to 1 centimeter. Okay, and this is x equal to 3 centimeters. It's symmetric with respect to the mean position. No? This is also 1 centimeter away from the mean position. This is also 1 centimeter away from the mean position. So whether it's going in this direction or this direction, it will have the same speed. If this speed is v prime, then here and here, both times it will have speed v prime, and that v prime we saw was that approximately 0.27 meters per second. Whereas the maximum speed at the center we saw was approximately 0.32 meters per second, like this. Okay, so this is the oscillation, back and forth oscillation that is happening. Okay, so of course we'll study more in detail about oscillations in a chapter called simple harmonic motion later. But right now what work energy can help us with is this thing. We can find out the speed as a function of x by using the work energy theorem. Okay, and that work energy theorem was very simple, that work done by F was change in kinetic energy plus change in spring's potential energy. So Fx was equal to half mv square plus half kx square. So this very easily gives us speed as a function of x. Okay, and from this we can of course analyze that x will be maximum when the speed becomes 0. So that is how we got that maximum displacement or maximum extension of the spring would be 4 centimeters. So it's oscillating between 0 and 4 centimeters. Okay, so let's try another version of the same question. Achha, by the way, before we come to the other version, the other option we could do, okay, we could also use work kinetic energy theorem instead of work energy theorem. So as the block is moving, there are two forces which are doing work on it. In total, there are four forces. Okay. But out of those four forces, only two of them are doing work. Okay. So you would have seen that the net work done is change in kinetic energy. So work done by mg is 0, work done by normal reaction is 0, but the work done by the spring force, it is integration of minus kx dx from 0 to x. So it is minus half kx square, because the spring force is acting in the negative direction, the displacement is in the positive direction. Work done by F is Fx. Okay. So net work done, this equation would have given us work done by spring plus work done by F equals to change in kinetic energy. So you would have got minus half kx square plus Fx is equal to half mv square. So that is why I say that there's no difference between the work energy theorem as such and the work kinetic energy theorem. There are two ways of saying the same thing, but always work energy theorem is more convenient. Why? Because here we have to calculate the work done by the spring using this formula. Okay. Whereas there we are using the direct formula for delta U. There we are just directly using the formula of the spring potential energy, which is half kx square. So we don't have to do this thing. We don't have to calculate work done by spring by integration method. We don't have to do this separately. Now, this is not required. We can directly use this. So that is why the work energy theorem method is more preferable for a system where we know the formula of potential energy. Okay. So that becomes another important thing. Now, also, we will see that there are various systems where if the work done by external forces is 0 and the work done by non-conservative forces is 0 for a system, which was not the case in the previous one, but suppose that happens, then the change in kinetic energy plus change in potential energy is 0. Okay. Or we can say that kinetic energy plus potential energy is constant because the change is 0, or total mechanical energy is constant. So for a system like this, we say that the mechanical energy is conserved. Okay. So for a system where we know that external forces are not doing any work, so two necessary conditions: external forces are not doing any work, and there is no non-conservative force which is doing work, we can directly say that mechanical energy is conserved. So this becomes a very important problem solving trick, or like a special case of application of work energy. Okay. Yes, Nikita, I'll show you that method again in the end, but okay, let's move ahead to this first. Okay. So for example, if I have a situation like this where what I have is a block against a spring like this. Okay. So the block is not attached to the spring. Block is just resting against the spring. Okay. It is not attached to it. Okay. Now suppose an external agent pushes the block by, let's say, x naught into the spring, that is towards left in the above diagram, towards the left side. Okay. And releases it from rest. Okay. Find the speed of the block when it loses contact with the spring. Okay. Assuming, of course, that this is a smooth surface. Now we can see here that from the time the external agent releases the block till the time the block has left the spring with some kinetic energy, if you think of the system consisting of the block plus the spring, then what is happening? Mechanical energy is conserved because the external agent has released it now, so he's not doing any work, and there's no friction, so there's no non-conservative force. So only spring force is doing work, and spring force is which type of force? Internal conservative force. So it will not be considered on the work done side, it will be considered on the potential energy side. So here what is happening is, initially your external agent has pushed the block against the spring, and released it from rest, such that the spring right now is compressed. It is at L minus x naught kind of position, but the block is released from rest. Okay. And as the spring pushes the block, the moment it comes back to its natural length, it releases the block. So the block goes off with some velocity v, and the spring is now back to its natural length. Okay. So between this position and this position, if we talk about the system being the spring plus the block, what is happening? There is no work done by external force. No, there is no work done by non-conservative force because there is no friction. So change in kinetic energy plus change in potential energy of the spring is zero. So going from this state to this state, what has happened? Your kinetic energy is increased by half mv square. Initial kinetic energy was zero because u was zero. Final is half mv square. But the potential energy, now what is happening in here? X of the spring is zero. So final potential energy is zero. Initial potential energy here is how much? It is half kx naught square. But the final potential energy of the spring here is how much? Is zero. So the change is minus half kx naught square. So this is zero. So logically, what we'll say that the kinetic energy of the block, it's come as a result of the spring giving it its potential energy. No external agent has done work. The spring has lost its potential energy and converted that into kinetic energy. So naturally, the speed comes by a very simple formula. It is x naught into square root of k by m. Okay. So it's directly proportional to the initial amount of compression that we've given the block. So this is a very simple example of the conservation of mechanical energy of a spring mass system, because it's on a smooth surface and there's no external force doing any work. This is unlike the previous question where the external agent was continuously applying a force. So there was work done by F. So वहाँ पे क्या था? Work done by F was change in kinetic energy plus change in potential energy. But here this is not there. So it's just this term is becoming zero. Okay, so this is a case of conservation of mechanical energy. Okay, so make a quick note of this and I will show you the previous question, second part also once more. Then we'll move on to some more interesting examples of conservation of mechanical energy. Okay, so I'll just take you to this theory part along with the second method of the last question where we use the work kinetic energy theorem instead of the work energy theorem. Then we'll come back to this question. Okay, so now let's take a relook at this question. So this one, as you can see, is a very simple situation. It doesn't get easier than that question. Okay, let's look at another example next. So this time we'll take a vertical spring mass system. So this block is suspended by a spring. Okay, so given information here is that the mass of the block is once again 5 kg. We'll take the acceleration due to gravity as 10 meters per second square, and the spring constant we will this time take as 20 Newton per centimeter. Okay. Now initially the block is at rest in equilibrium. Okay, so the first thing we'll do here is find the extension of the spring at equilibrium. Okay, for the block. Now next, what is happening? Somebody pushes the block up from the equilibrium position. So an external agent lifts the block up by 2 centimeters from equilibrium. Okay, and releases it from rest. So what we have to do now is find the speed of the block when the spring is at an extension of 2 centimeters, 3 centimeters. Find the maximum speed of the block and find the maximum extension for the spring. Okay, so this is a slightly trickier question. Be careful when you're solving it. Start with the first part. Tell me how much is the extension of the spring when the block is initially just resting in equilibrium. Yes, that's correct, Kevin. So once you realize that, you also know that your external agent is, yes, Aman, that's correct. So you're pushing it up by 2 centimeters from there and then releasing it from rest. So you know what is the initial state of the spring, therefore. When you are releasing it, now you know what is the initial state of the spring from which you are releasing it. Okay, sorry, this is the second part. This will be the third part. This is the fourth part. Okay. So when you are releasing the block, after lifting it up by 2 centimeters, what is the state of the spring at that point of time? Is it at natural length? Is it at mean position? I mean, is it extended? Is it compressed? No, it's extended only. It's not compressed because you're lifting it up by 2 centimeters. No? Yeah, Amog, your answer is correct for the first part. It is extended by how much? By half a centimeter. Okay. It is extended by half a centimeter. So that is what you use when you apply the work energy theorem for the second part. Okay. So let's understand this in detail. So see what is happening. Initially, my system was in equilibrium. So at that point of time, the weight of the block was being balanced by the spring force. That is how we'll find the equilibrium condition. So to find the equilibrium state of the spring, the extension of the spring in equilibrium, you have to understand that in the equilibrium state, equilibrium का मतलब ही क्या होता है? Net force is zero or acceleration is zero. Okay, so spring force, let's say kx naught, has to balance mg. So the compression of the spring in equilibrium, sorry, the extension is mg by k, which when you work out here will be 2.5 centimeters. Okay, so in this state, the spring has an extension of x naught, which is 2.5 centimeters. But now my system is not starting from here. अभी मैं क्या कर रहा हूँ? यहाँ से I'm lifting the block up by 2 centimeters. ना? So I'm taking the block to this position, where in comparison to this is lifted up by 2 centimeters. Okay. So when it is lifted up by 2 centimeters, let's say at that point of time, my extension of the spring is x1. So how much is x1? It is 0.5 centimeters. And I'm releasing the block from rest. So this is the situation. Okay. So naturally, the moment I release it, it will have a downward acceleration because now mg will be greater than kx1. So it accelerates downwards. Okay. So this is what happens. So anyway, the answer to the first part of the question was this. Okay. Now we are coming to the second and third part. So this is the starting of the motion. So this is the second part. This is the starting point because your external agent is lifting it up by 2 centimeters and releasing from rest. So at the starting point, the extension of the spring is 0.5 centimeters and the block is at rest. Understood now? So this is very important to understand here. Okay. Now we want to do what? We want to find out the speed of the block when the extension of the spring has become how much? For the A part, we want to make the extension of the spring 2 centimeters. Okay. So from 0.5 centimeters to 2 centimeters, we have to understand what's happening. So as the block now goes from here to this state, actually it will be a little bit above this. because the extension of the spring is going to 2 centimeters. The block will be somewhere here, let's say. So now what is happening? The state of the spring is at L plus x2, let's say, where for the A part we are taking x2 as 2 centimeters. Okay. So at this point of time, the speed of the block is some. So if you compare what is the displacement of the block from here to here, from this position to this position, what is the displacement of the block? The downward displacement of the block S will be equal to x2 minus x1 downwards. Okay. So again, if I'm specifically referring to my part A, the displacement of the block when x2 is becoming 2 centimeters is 1.5 centimeters downwards. Okay. So now I have to apply work energy theorem. So for that, so the first thing I'll need to do is I'll have to define my system. So the most convenient thing to do here would be to take my system as the spring plus the block plus the Earth's gravitational field. Okay, because then what happens? Both the forces acting on the block, the spring force as well as mg, they are internal conservative forces. Okay, so there is no work done by external force. There is no non-conservative force to do work. Okay, so change in kinetic energy plus change in spring's potential energy plus change in gravitational potential energy of the block is zero. There is conservation of mechanical energy. Okay, so I get a simple formula over here that going from this initial state to this final state, what is the change in kinetic energy? It's half mv square, because I started from rest over here. What is the change in potential energy of the spring? It is half k x2 square minus x1 square. And what is the change in gravitational potential energy? Minus mgs. Okay, because this thing, it's a downward displacement, so this should be zero. So I get a simple formula that the kinetic energy at any point of time is equal to mgs minus half k x2 square minus x1 square. Now remember, s was also equal to x2 minus x1. So I get the simple formula that the kinetic energy is equal to mg into x2 minus x1 minus half k into x2 square minus x1 square. So in this always we'll be substituting x1 obviously as 0.5 centimeters, but x2 will be substituted as 2 centimeters for part A. X2 will become whatever 3 centimeters for part B, and so on and so forth. Okay, so let's do this calculation next. So for the A part, this will become mg multiplied with 1.5 into 10 raised power minus 2. Okay, minus half k. Now the spring constant was how much? It was again 20 newtons per centimeter, right? So 2000 into x2 square. Now x2 was 2 centimeters, So that will become 4 minus x1, which is 0.5. So 0.25, but there will be a factor of 10 raised power minus 4 because we are converting the centimeter square to meter square. So half mv square will be mg into 1.5 into 10 raised power minus 2 minus, so become 3.75 into 10 raised power minus 1. And we can just substitute the value of m now. So it's 5 kg. So you can see v square will become 2g into 1.5 into 10 raised power minus 2 minus this term, which is basically 0.375 into 2 by m. So 2 by 5, 0.375. So v square is, this is 20 into 1.5 into 10 raised power minus 2. So that is 30 into 10 raised power minus 2. So 0.3 minus 0.375 multiplied with 2 by 5. That's 0.15. So we'll get v as square root of 0.15, approximately 0.39 meters per second. So you can take down the calculation later, but first of all, make sure you have understood this, because the same formula we'll be using for each of the parts. Only x2's value will keep changing. So the main thing is this thing, the application of work energy theorem, and in this case, conservation of mechanical energy. How we are applying the conservation of mechanical energy. Yeah, good, Aman. Okay, so for the B part, you just substitute as 3 centimeters instead of 2 centimeters, and you'll get some different answer. Or interestingly, I think you'll get the same answer because it's symmetric with respect to the equilibrium position. Anyway, we'll discuss. Yeah, it's symmetric with respect to the equilibrium position. So we'll actually get the same thing for the B part also. The method of calculation will be different, but the final answer will be the same. So in the B part, you will again substitute this only, this formula only, but you will substitute x2 this time as 3 centimeters. Whereas x1 was 1 centimeter only. Rest all the things are same. You will interestingly get v as the same thing, square root of 0.15. And I'll explain why it has to be the same when we discuss about the whole motion in more detail. I'll explain why it's the same. But just take down this calculation also and just double check my calculation once. You can do the B part later. So in this, of course, I'm substituting in the end m as 5 kg and k as 20 Newton per centimeter. So that's actually 2000 Newton per meter. So this value and this value we are substituting, and of course g as 10. Okay. Now apart from that, x1 and x2. And for b part, x1 and x2 will be like this. Sorry, x1 is still 0.5, my mistake. X1 is not 1, x1 is 0.5. Going from the same initial state, but now we are taking the point of time when we are finding v as an extension of 3 centimeters. All right, so this is clear. Now let me explain how we will find the maximum speed and the maximum extension of the spring. See, again, what is happening is our initial state was this, where x1 was 0.5 centimeters. So you can see that x1 is a lot less than mg by k. So right now what's happening, it's accelerating like this, starting from initial 0. Now from this till it goes to a state where this becomes L plus x naught, where you'll remember x naught was 2.5 centimeters. Okay, till it goes from this state to this state, what is happening? The speed is increasing. Okay, so that means from x1 equal to 0.5 centimeters to the equilibrium position 2.5 centimeters, the acceleration is downwards. Basically what I'm saying is when x is less than x naught, okay, kx is less than mg now. So that's why the acceleration is downwards from here to here. So what is happening? The speed is increasing. Okay. Whereas the moment it crosses this point, so by the time it reaches here, it has maximum speed. But the moment it crosses this, and now it goes to some x which is greater than 2.5 centimeters or mg by k. Now the moment it comes to this kind of a state, some general state like this, where x is greater than x naught, or x is greater than 2.5 centimeters, or x is greater than mg by k. Now what is happening? Kx is dominating. So it will start decelerating again. So it starts decelerating. So that is why it will reach the maximum speed at what value of x? At the equilibrium value of x, that is x naught equal to 2.5 centimeters. Okay. So from this we understand that from x equal to x1, which was 0.5 centimeters, to x equal to x naught, which is 2.5 centimeters, the block will accelerate. So at this point, it will have maximum speed. V will be maximum. Whereas this was the starting point. So here the speed was 0. Okay. And then from x equal to x naught, okay, to whatever the maximum this extension is, it will decelerate. Such that finally when it comes here, its speed becomes 0. Okay. And it will do a vertical oscillation. After it reaches here at the maximum extension, it will come back to the equilibrium position, increasing speed, then go up further up to x1, okay, where the speed decreases. So it will keep going up and down. And every time it's at the highest point, the extension of the spring will be 0.5 centimeters and speed will be 0. Every time it's at the lowest point, the speed will again be 0. But every time it's at the midpoint of the highest and lowest point, that is at x naught, the speed will be maximum. Okay, so this is what we understand logically by just interpreting the relationship between the forces, the free body diagrams. Yahan pe mg is dominating over kx, so it is accelerating downwards. But at this point of time, mg and kx just balance each other. Okay, and now kx dominates over mg, so it starts decelerating. So logically, as you're going from acceleration to deceleration, the switchover point where your acceleration becomes 0, that is your equilibrium point, that is when your speed becomes maximum. So from this we know that the speed will be maximum. Therefore, v is equal to v max at x equal to x naught, or mg by k, which is 2.5 centimeters. So we can now go back to that equation, that half mv square, but we'll substitute this as this is equal to mgs, which will now become x naught minus x1, okay, minus half k x naught square minus x1 square, because we'll substitute x2 as x naught, so v is becoming v max, okay, in the work energy equation that we had written above. And you can see that in this equation that we had written above, in this equation, this was our work energy relation. So in this work energy relation, when we substitute x2's value as x naught, we should get v's value as v max. Okay, so this is what we've done here. This is the work energy relation or conservation of mechanical energy relation, but with this thing substituted. Okay, so as you can see, v max square will become 2g into 2.5 minus 0.5 into 10 raised by minus 2, okay, minus spring constant was 2000 by 2, okay, and this 2 cancels out because of half m, so divide by the mass, which is 5 kg, okay, into 2.5 square minus 0.5 square into 10 raised by minus 4. So v max square here is becoming 20 into 2 into 10 raised by minus 2 minus 2 by 5 into 6.25 minus, so that will become 6, right, into 10 raised by minus 1. So this is becoming 0.4 minus 0.24. This just check my calculation if this is correct. Okay, so we are getting v max is equal to 0.4 meters per second. So it's reaching a maximum speed of 0.4 meters per second, but it reaches that at x equal to 2.5 centimeters, or this thing, the equilibrium position. Okay. Now symmetry should tell you that it will go further down by the same distance as it had come down from the starting point to equilibrium. So starting point to equilibrium is come down by how much? By 2 centimeters. So it will go further down also by 2 centimeters. So that symmetry is telling us that our maximum extension of the spring should come out to be how much? 2.5 plus 2, or 4.5 centimeters. But we will show that from the calculation also. Okay, so this was our starting point where u was 0. So x1 was 0.5 centimeters. Now from here to the position where we have maximum speed, that is the position of 2.5 centimeters. Now, so here to here is how much? It is 2 centimeters. So symmetry is telling us it should go to the lowest position where again speed will become 0, but x maximum kitna hoga? So that will be again 2 centimeters below. There's always a mean position in an oscillation with respect to the extreme positions are symmetric. If I just go by that principle of symmetry, they should be 2 centimeters further below. So I should get x maximum as x naught plus 2 centimeters. So that is 2.5 plus 2 or 4.5 centimeters. However, we will verify this from the equation also. Okay, so if you're done with this part, just try to verify this result that I've got by using work energy relation. I've just used the symmetry here. This is the symmetry of the vertical oscillation. No, so if I took the block 2 centimeters above the equilibrium and released it, the furthest it should go is on the other side of equilibrium, that is below the equilibrium by 2 centimeters. No, so it keeps oscillating between 2 centimeters above and 2 centimeters below. And as it oscillates, every time it crosses the mean position in between, it has this maximum speed of 0.4 meters per second. Every time it reaches the highest point or lowest point, it's at rest momentarily. Yeah, so that thing again we can see that if we apply in work energy theorem also, we'll be able to verify this result. That so now we can verify this by making use of the conservation of energy equation or the work energy relation. So for the last part of the question, we wanted to find x maximum. So x will be equal to x maximum when the speed of the block becomes 0. It comes to rest momentarily, stops momentarily because then it will accelerate upwards after stopping. So we had that half mv square was mg into x2 minus x1 minus half k into x2 square minus x1 square. This was there. So in this we will substitute v as 0, x2 as the x maximum which we are trying to find out, whereas x1 is 0.5 centimeters. Okay, so when we substitute, we'll get like this, that mg into x maximum minus 0.5 minus half k into x maximum square minus 0.5 square. This should be 0. Now this is rather easy to solve because we can just take like this. We can take this thing common. Okay, using the formula that a square minus b square is a minus b into a plus b. So make use of that here. So this will give us two roots. One root is x equal to 0.5. That is not okay because that is x1. The other root is this thing, mg minus half k into x plus 0.5 is 0. So that means mg or 2 mg by k is equal to x plus 0.5. So this x should be equal to 2 mg by k minus 0.5 centimeters. Now 2 mg by k you can see is twice of 50 newtons divided by 20 newtons per centimeter. We can go back to this hybrid unit system. So you can see what it becomes here. So it becomes 5 centimeters minus 0.5 centimeters. So as expected, this x is only the maximum x. It is 4.5 centimeters. Okay, so this is a simple case of, again solving that specific equation. I mean, solving that general equation for the specific condition that whenever the spring reaches its maximum extension, the block should be momentarily at rest because it's oscillating up and down like this. So at the lowest point, the block is momentarily at rest. Okay, so hope this application is clear to all of you. Okay, now let's pick up a question where again we bring friction into play. So now just so that the calculation is easy, I'm picking up a question directly from H.C. Verma. If I'm not mistaken, this is question 42 or 44, something like that. I'll give you a list of the questions also which you can work out after today's class. So we have a rough inclined plane like this, whose inclination with the horizontal is 37 degrees. And at the end of the inclined plane here, there's a fixed wall with a spring attached. So it's spring constant K. And this is a rough surface. So it has some coefficient of friction mu. Now what we're doing is a block is released from rest from this position E, let's say over here. So when it is released, it is at a certain distance D from the spring. Okay. So now the data given to us about the question is like this, that mass of the block is 2 kilograms. Okay. Acceleration due to gravity we have to take 10 meters per second square. Okay. And the initial distance of the block from the spring, that is 4.8 meters. Okay. So the block is released from rest at d equal to 4.8 meters from the spring's tip or the end of the spring, that thing. Now what happens is, after sliding down, okay, and hitting the spring, okay, or making a collision with the spring, it compresses the spring by a maximum compression of 20 centimeter. Okay, so the maximum compression for the spring is 20 centimeters, and thereafter makes a displacement of 1 meter again before stopping momentarily. Okay, so the block comes, hits against the spring, compresses it by 20 centimeter, and then again slides up the inclined plane because the spring is pushing it back. And when it slides up the inclined plane from where it compressed the spring, it makes a displacement of 1 meter precisely before coming to rest again momentarily. Okay, so from this we have to find both the unknown quantities, the coefficient of friction and the spring constant. Both these things we have to find out. So this is a very key question to understand the application of work energy theorem and also how to use it efficiently. So just try to set up the work energy equation here. I'll explain in a moment. Yeah, so this is actually question number 43 of HC Verma. Okay, so when we are approaching a question like this, the first thing we should do is we should have clarity about what we are applying work energy theorem for. In other words, what is our system? We should have clarity about that. So the first thing here we'll see is that we should take our system to include maximum number of conservative forces. So that will happen if I take the spring also as an internal conservative force and the gravitational force also as internal conservative. So that will make life simple when we are solving. So we should take our system as the block, okay, plus the Earth's gravitational field, or what we can say as the Earth's gravity, plus the spring. So when we do that, then for the system we can say that work done by friction is equal to change in kinetic energy plus change in spring's potential energy plus change in gravitational potential energy of the block. Because normal reaction is the only external force and work done by normal reaction is zero. And work done by friction That is the work done by the non-conservative force. No, wedge is not movable, beta. It's a fixed inclined plane. The inclined plane is fixed. Understood, na, Sikita? Here, this is not a movable wedge. It's a fixed inclined plane. Yes, it is always, it's not necessary. But then see, if we don't include gravity in our system, Aman, then we have to consider work done by gravity. Okay. But we already have formula for gravitational potential energy. Na? So why we separately want to write work done? Okay, so this is a fixed inclined plane. It's a fixed rough inclined plane. So the inclined plane is not going anywhere. So okay. So now see what is happening. Initially, our block was here at rest, such that this distance we know. This is 4.8 meters. And this angle we know is 37 degrees. Okay. Now let us look at the system at the next moment when the spring has maximum compression. So when the spring has maximum compression, let's say the block is at the position B, its speed becomes 0. Because now the spring has maximum compression, or L minus 20 centimeters. Whereas here the spring was at a length of L. Okay. So if you compare with the initial position where the block started, how much it has displaced by now? It has made a displacement of that distance d plus x maximum. So 4.8 plus 0.2 of 5 meters. Okay. And what is the vertical component of that displacement? So that is h1. So this angle being 37, it is that s sine 37. So 3 meters, because s is 5 meters. Now during this entire journey going from here to here, what is happening? Kinetic friction acting on it is mu mg cos theta. Okay, so for the journey from A to B, when I write this, work done by friction is change in kinetic energy plus change in spring's potential energy plus change in gravitational potential energy. Work done by friction will be minus mu mg s. Okay. Change in kinetic energy will be 0 because our V is also 0 and our initial U was also 0. Okay. Change in spring's potential energy is plus half k x max square, and change in gravitational potential energy is minus mg h1 because the vertically downward displacement is h1. So let's see what this gives us. This gives us an equation minus mu into 20 into 5. Okay. Weight of the block was 20. Okay. Is equal to half k x maximum square. I'll put the x max later in this, minus again 20 into 3. So I'm getting this relation that minus 100 mu is equal to half k x maximum square minus 60. This is my equation 1, which I'm getting by applying A to B, work energy theorem from A to B. Now I also have the second part of the journey. Once it stops here momentarily, the spring pushes it back. So now when it pushes it back, how it's going? It's going from that state where it was at B to, let's say, this position C, where it comes to rest again. But this time the displacement is 1 meter. So just set up an equation for B to C. I'll just get back. So this next part of the motion, if you see from B to C, what is happening is now when the block is at C, the spring is back to natural length position. And the block is at rest at C. Okay, the spring is back to natural length position, but the block had started from somewhere here. This was the position P. And so that is why from B to C, this displacement, this is 1 meter. And therefore, now again when it is on its way up, this time friction is acting down on it. No? So when it's on the way up like this, kinetic friction is acting this way. Mu mg cos theta is acting this way. Okay. And again the vertical displacement, say we write it as h2 this time. So this being 37, it is going to be 0.6 meters. 1 into sine 37 will be 0.6. Okay. So if we write the work energy theorem from B to C, we'll get this relation that work done by friction, that will become minus mu mg cos theta. This will not change the sign this time, because even though the direction of motion has become upwards, but friction has become down the inclined plane. So this will always remain negative. So minus mu mg cos theta s prime is equal to the change in kinetic energy, which is again 0, because here also at C also the block is again at rest. At B also it started from rest. Okay. So that is 0 plus change in potential energy of the spring. Now this time the change in potential energy of the spring is minus half kx square. Why? Because here x is 0 in the final state, whereas when it started from B, x was x maximum. Okay. Plus change in gravitational potential energy. So this time it is plus mg h2 because it's going up. So this equation becomes minus mu into, oh sorry, I forgot the cos theta. That's what I was thinking. The cos theta is 4 by 5 into 1. Okay, so please make a correction here also. I forgot the cos theta. So the work done by friction is minus mu mg cos theta s. So it is minus mu into 20 into 4 by 5 into 5 meters. So this will actually become 80 mu. Let's make a small correction here. This will be minus 80 mu. So instead of 100, this term here will be 80 mu. Likewise here, plus 20 into 0.6. So we'll have this equation that now minus 16 mu, right? is equal to minus half k x maximum square plus 12. This is our second equation. So compare it with our first equation and we'll be able to solve for both the unknowns. Compare this equation and this equation, this one. So just add the two equations and your half kx square goes away. So minus 80 mu on this side minus 16 mu on this side is equal to minus 60 plus 12. So we get minus 96 mu is equal to minus 48. So mu is coming out to be 1 by 2 or 0.5. Okay. And then substitute that mu over here. So minus 16 into half is equal to minus half kx maximum square plus 12. So half kx maximum square is becoming 12 minus 8 or 4. So half k into 0.2 square is equal to 4. So you get k in SI unit as 4 into 2 divided by 0.4. So 0.04. Okay. Or we can simply write this as 4 into 10 raised power minus 2. So this will become 200 Newton per meter. That will become the spring constant. Okay. So this is a very important application. This is a very key question to understand the application of work energy theorem in any system where these three things are involved: spring force, gravitational force, or spring potential energy, gravitational potential energy, plus also work done by friction. And you can see that friction is a non-conservative force here because its direction is changing as the direction of motion is changing. Okay. Now, when you're analyzing this question later, you can do one more thing. You can solve for the entire journey ABC. You can also write, try using the work energy theorem for the path A to B to C. So if you do that, now it's very interesting. Your change in kinetic energy will also be 0. Change in springs potential energy will also be 0. But change in gravitational potential energy will be a negative quantity and work done by friction will be a negative quantity. So from that you will get mu directly. But when you are calculating work done by friction, you have to be careful. You have to break the motion into two parts, A to B and then B to C, because in between the direction of friction is changing. Okay, people, so hope this is clear to you. Now about some practice questions. So you can go through the H.C. Verma solved examples first of all. Okay. So I'm giving you some work which you can do in the next couple of days before the test comes up. So first of all, revise all the questions I've done in class, particularly lecture 2 and 3, like last time's lecture and today's lecture. Then for practice, do H.C. Verma solved examples from work power energy chapter. So go through the solved examples straight from 1 to 6, and then again 8, 8 to 12. Go through this. Then in the main exercise, you can do questions. Then skip a few questions because there's a concept of power which we will discuss in the next to next lecture. And 43 is in fact a question we've just done in class. So these are questions you can go through in the next couple of days. You'll not have difficulty. They are, I mean, quite simple questions. Once you understand the statement and application of work energy theorem, you should not have difficulty with these questions. And also make sure to go through the questions I've done in class, both in today's class and last week's lecture. At least these two lectures, make sure you revise all the questions. So that way you will be able to solve the questions in the upcoming test quite easily. Okay. So yeah, so as far as work by energy is concerned, in the upcoming major test, it is going to be up to this portion that we've just discussed. Okay, that is up to the application of work energy theorem, conservative, non-conservative forces, potential energy, and work energy theorem, up to this portion. So that's it for today's session, people. Wish you all the best. I will send you these notes along with the recording very soon, so you can refer to this.